Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving into a fascinating piece about reverse engineering and cryptography in early software development, specifically focusing on a DOS-based word processor called Qtext. It's a deep dive into the 90s, when things were different.
Sounds intriguing. So what exactly was the problem they were trying to solve?
The core issue was a client had a bunch of locked Qtext documents from the mid-90s, and they'd lost the passcodes. Qtext, written in Turbo Pascal, was a Hebrew-English word processor. The authors, neither of whom had even touched a reverse engineering tool back then, had to figure out how to unlock these files. Quite the challenge, right?
Definitely a blast from the past. What were their initial steps in tackling this problem?
First, they got their hands on working Qtext binaries and fired up DOSBox, the emulator. They played around with the encryption feature and quickly realized a few things. The passcode was short, only 4 characters, uppercase letters and numbers only. That's a pretty small key space. Locked documents had a specific header, hexadecimal 1D, and the variable part of that header, 16 bytes, seemed to correlate directly to the passcode. No salt either.
So, no salt, a small key space, and a header that seems to contain the key. Sounds like a potentially weak system.
Exactly. They also noticed the encryption seemed to work on a per-line and per-column basis, skipping spaces. This gave them some clues about the encryption mechanism, but they decided to focus on the key derivation algorithm. They figured brute forcing was simpler if they could quickly test passcodes, assuming that 16-byte key in the header was derived from the passcode.
Makes sense. So how did they go about reverse engineering the key derivation algorithm?
That's where things get interesting. They had to deal with MS-DOS binaries, which operate in real mode. No PE files here. They were DOS-MZ executables, packed with pkzip as a self-extracting executable. Finding tools to unpack it was a whole adventure in itself.
pkzip, huh? I remember that. So, did they manage to unpack it easily?
Not at first. They tried the DOSBox debugger to step past the unpacker, but that only got them a small part of the code. Then, they went on a hunt for generic, executable unpacking tools from the old cracking sites. Remember those? Eventually, they found a blog post that led them to Xtools, and DISLITE version 1.15 finally did the trick.
Ah, the joys of retro reverse engineering. So, with the binary unpacked, what was the next hurdle?
Memory overlays. The executable used Turbo Pascal's memory overlay system. Since they were in real mode, paging wasn't an option. The code was split between a root segment in the .exe and overlays in a .over file. The overlays were swapped in and out of memory on demand using int3f interrupts.
Overlays! That sounds like a nightmare to debug dynamically.
You're not wrong. IDA-free 5.0 helped with static analysis by flattening the stubs. But dynamic debugging was tricky because the overlay locations kept changing. They eventually found a clever workaround, breaking on overlay to root calls and stepping out into the newly loaded overlay.
Smart move. So, with the debugging environment sorted out, how did they find the key expansion function?
It took some serious tracing. Initially, they tried hotspot analysis by repeatedly failing the passcode check. But they switched to a more direct approach, setting a breakpoint on the int21 interrupt handler to catch open and read calls. This helped them trace the document opening and header reading, eventually leading them to the function that takes the passcode and header as parameters.
Okay, so they found the function. What did they discover about the key derivation process itself?
The passcode goes through a permutation function. Each byte is iteratively incremented by the sum of all bytes in the string. But there's a twist. After each increment, the byte value is checked against a bitmap. If the value is invalid, it's incremented by 0 by 22 to make it valid.
A bitmap check. That's an interesting way to validate characters. So what's the actual permutation function look like?
It's relatively simple. Each byte is incremented by the sum of all bytes in the string, modulo hexadecimal ff. Then, if the resulting byte isn't within the valid range, it's incremented by 0 by 22. After that, the string is concatenated to itself 3 times and passed through the permutation function again. The result is the 16-byte key in the header.
So it's a permutation function applied twice with a concatenation in between. Sounds like it could be reversible, but probably not trivial.
Exactly. They realized the permutation is linear, but the overflow introduces nonlinearity, Reversing it involves dealing with multiple possible solutions at each step. They used a recursive decomposition algorithm to handle the branching.
Recursive decomposition sounds computationally intensive. How did they manage to keep the search space manageable?
They used two key constraints. First, any decomposed byte had to be a valid passcode character, an uppercase letter or numbers. Second, the 16-byte key before the second permutation was just a 4-byte sequence repeated 4 times. This meant they only had to decompose a 4-byte suffix and check if it matched the original key after permutation. This narrowed the search space down significantly.
Those constraints are crucial. So how did they put it all together to crack the passcodes?
They started with the 16-byte key from the document. They ran it through the decomposition function to get all possible 4-byte suffixes. Then, they fed those suffixes back through the permutation function to find the correct one. Finally, they ran the resulting suffix through the decomposition function again, narrowed down the results to valid passcode characters, and voila! They had the original passcode.
That's a pretty impressive feat of reverse engineering. So what's the takeaway from this whole experience?
It's a fascinating look at early software development and cryptography. It highlights the challenges and limitations developers faced back then, and how they came up with creative solutions. It also shows how far cryptography has come since then. Plus, they released a Python script called qtext_cracker.py on GitHub, so anyone can try it out.
Definitely a great example of how reverse engineering can help preserve knowledge and unlock forgotten secrets. Thanks for walking us through this. It was really insightful.
My pleasure. It's always fun to delve into these kinds of projects. That's all the time we have for today. Thanks for tuning in to Tech Bytes and News. We'll catch you next time. Opening parentheses. Closing parentheses.
Bye-bye.